Hello, my name is Shahriari, and this is a lecture in a series of lectures on introductory combinatorics based on my book An Invitation to Combinatorics. The subject of this lecture is Eulerian trails and circuits, and this is a part of the graph theory part of these lectures. So let's get started. What are we going to do in this lecture? I'm going to talk a little bit about Konigsberg and its bridges. That's where this problem started out with. And then we will define Eulerian trails and circuits. We will prove that if the degree of each vertex in a graph is positive and even, then every vertex lies on a circuit. We also will prove that a finite general graph with no isolated vertices has an Eulerian circuit, whatever those are. I will define that in a moment. If and only if connected all degrees even. And we'll prove also that we can decompose every circuit into cycles, and the finite general graph can be decomposed into cycles if and only if every vertex of G has even degree. As a final example, we'll ask the question, what's the minimum number of disjoint trails covering all edges of K8? Konigsberg was founded in the 13th century by the Teutonic Knights during what's now called the Baltic Crusades or the Northern Crusades. It has very many famous citizens, including mathematicians Christian Goldbach and David Hilbert. They were both born there, and Leonhard Euler worked. But Immanuel Kant was also born in Konigsberg and lived most of his life there, went to university there, was a professor there, and wrote the Critique of Pure Reason there. The political philosopher Hannah Arendt wasn't born there, but moved there when she was 3 and spent some time there also. Konigsberg, before World War II, was the easternmost big city in Germany. During World War II, it was leveled and completely destroyed by Allied bombings. And after the war, it was annexed by the Soviet Union. Today, it's Kaliningrad, and it's an exclave of Russia surrounded by Poland and Lithuania. In the early 18th century, there was a river Pregel through the city that had 7 bridges. And the citizens always asked, is it possible to start at one of the banks, go over every bridge exactly once, and return to the original point? Now, Euler in 1736, he was living there, solved this problem and generalized the question. In fact, most people think of this as one of the first papers in graph theory in the Western tradition. So let's translate this problem to graph theory. For each of the banks and islands, you put a vertex. So there are 2 islands and 2 banks, the northern bank and the southern bank, and you put 4 dots, 1 for each of those. And then for each of the bridges, you put an edge. And what you end up with is a multigraph. A multigraph when you allow double edges, and you have 4 vertices and 7 edges. And what does the question become? The question becomes that, is it possible to start at one vertex, go through every edge exactly once, and be back at the original vertex? And you can answer this very quickly by trying it. Spoiler alert, the answer is no. But the more general question is that, how can you answer questions like this for other kinds of graphs? This is similar to a problem that you might be seen when you were in 3rd grade. Can you draw this house without taking your hand off the paper? Can you start at a point, draw this whole thing without repeating any edges, and by coming back to the original place, or maybe not even coming back to the original place? Can you draw this without retracing any of the edges and taking your hand off the paper? So maybe you can't do that. In fact, you cannot do that. Then the next question would be, what is the minimum number of times that you have to take off your hand off the paper? You take your hand off the paper to draw this house. The answer is interesting. It's interesting that we can actually come up with a theorem that answers this completely and easily. But in graph theory, like much of mathematics, but especially in combinatorics, what's more interesting than the actual answers is the concepts and techniques of proof. If you become a mathematician, what you're learning is really a group of techniques that you can apply to different situations. Any one theorem will apply to just one little specific situation, but techniques are things that you can apply to different things. And so you want to really be paying attention to the concepts and techniques. And those are much more important than the actual answers. So first, I want to give you some definitions. These were subjects of previous videos. If you haven't seen any graph theory at all, then you might want to watch those other ones. Although I will briefly remind you of all we need here as well. So a general graph is a graph that means a bunch of vertices and a bunch of edges joining those vertices, where we allow repeated edges and loops. So loops are allowed, like this loop E1, and between 4 and 5, I have two edges, E2 and E3. A walk from one vertex to another is when you start at a vertex and go to an edge, through an edge that's incident with that vertex, then you get to another vertex, then you go to another, through another edge to another vertex, and you just keep going. You can repeat vertices, you can repeat edges, and that's called a walk. So for example, you can start at 5, then go through the edge E2 to 4, and then you get to 4, and then from 4 you go to E3 and you're back at 5. Then you use the edge 5, 6, and you get to 6. Most edges, if they're a single edge, you can just think of them as a pair of vertices, 5, 6, and there won't be any ambiguity. But when you have double edges, you might need a name for them so that you know which one of the double edges you're traversing. After 6, you will take the edge 6, 7 to 7. Then you take the loop E1 back to 7, and then you take the edge 6, 7 back to 6. And so if you do this, start with 4 and go through this walk, you end up at 6, and this is a walk from 5 to 6. And again, in a walk, you can repeat vertices, you can repeat edges. Here, for example, we repeated the edge 6, 7 twice. If you don't repeat any edges, then that's called a trail. For example, a trail here would be if you start from 5, go to 4 via E2, then you go to 5 via E3, and then you go to 6, and that would be a trail from 5 to 6. A closed trail is called a circuit. Closed means that the beginning and the end vertices are the same. Or a circuit is a walk where you start at the same place, end at the same place, and there's no repeated edges. You can repeat vertices, but not edges. So for example, here, we start at 5, go to 4, then back to 5, then to 6, to 2, to 1, and back to 5, and that's a circuit. A circuit that has no repeated vertices is a cycle. So for example, 5, 6, 2, 1, 5 would be a cycle. Now, if you don't repeat vertices, you can't repeat edges either, because if you repeat an edge, then you will have to repeat its vertices as well. So these are some vocabulary, again, subject of previous videos where I gave more examples and discussed them in some more detail. So let's say a little bit more about trails and circuits. I might ask you, here's a graph. Is this graph just one circuit? Is this just a circuit? And the answer is yes, it is, because you can start at any one of them. Say for example, 1 to 2 to 3 to 4 to 5, back to 3 and to 1. And you can, again, start at any vertex, draw the whole graph, end at the original vertex without repeating any edges. That's what it means. And so this tells us that this is the kind of thing that we want to be asking about graphs in general. Are they just one big circuit? And such things will be called Eulerian circuits in the next slide. But what about this graph? This might look a little bit similar to the previous one, but this one is actually not, the whole graph is not a circuit. It has plenty of circuits in it, but the whole graph is not a circuit. You can't start at any vertex, draw all the edges, and get back to the same place without retracing any of the edges. You can try that, and you won't be able to do that. You will be able to come up with an open trail that covers the whole thing. So you can start at 3, go to 1, go to 2, then to 4, to 3, and then to 2, and you will have drawn the whole graph, but you didn't start from the same place, ended at the same place. So this graph, this whole graph, is not one circuit, but it is one open trail. So now I'm ready to define Eulerian trails and circuits, and I pretty much just did that. So an Eulerian trail is a trail that contains every edge. If you have an Eulerian trail, that means that you can draw the graph without taking your hand off the paper and without repeating any edges. If I change this graph a little bit, then it will have an Eulerian trail. I can start at 4, go to 5, then go back to 4, then go to 3, then go to 2, then to 1, then back to 5, then to 6, then to 2, then to 7, and then do the loop, and I'm done. And I've drawn everything. I've repeated some vertices, but I didn't repeat any edges, and I covered the whole graph. So this graph has an Eulerian trail. Now, an Eulerian circuit is a closed Eulerian trail. The trail that we had started at some place at 4 and ended at 7, did not begin and end at the same place. But if I can begin and end at the same place, then I have an Eulerian circuit. And this graph does not have an Eulerian circuit, but if I add one edge, then it will. So again, an Eulerian circuit is when you start at the vertex, draw the graph without taking your hand off the paper, without repeating any edge, and end at this starting vertex. And so again, if I add that edge 4, 7, then of course I will have an Eulerian circuit, because I had an Eulerian trail going from 4 to 7, and now I will take that final edge from 7 to 4, and I will have my Eulerian circuit. Now, an Eulerian graph is a graph with an Eulerian circuit. And I want to remind you what the degree of a vertex is. The degree of a vertex is the number of edges incident with it. The number of edges that come out of any vertex, that's called the degree. But note that a loop contributes 2 to the degree. So we think of that as the loop comes out of the vertex and then goes back in, adding 2 to the degree. The theorem that I want to prove is that if you have a finite general graph, a graph with finite number of vertices, but you allow, if you want, loops or double edges, and assume that every vertex's degree is even, so it's 0, 2, 4, 6, 8, and positive, so actually not 0. So the degree of every vertex is positive and even, so it's 2, 4, 6, 8, 10, and so forth. And then I will claim that every vertex will be sitting on some circuit. Now, this circuit might not be an Eulerian circuit, it might not cover the whole graph, but there will be for every vertex, there will be a circuit that it will be on. And again, what you want to pay attention to is the proof, like what is the technique that allows me to prove this? And the proof is actually a very straightforward idea. Start with that vertex V, with one of the vertices of the graph that you want to show that it's on some circuit, and you go from there. By the way, the fact that the degree is positive and not 0, all that's saying is that we're not allowing any isolated vertices, any vertices just sitting there alone with no edges. So you start at your vertex V and you take a walk. You keep walking. And the only rule that we want you to follow is that do not repeat an edge. So start at V and start walking through edges, but never repeat any edge. So what might happen? The graph is finite, so you'll have to get stuck. At some point, there won't be any more edges to use, and you will get stuck. But where will you get stuck? The point is that if you get to any vertex other than V, then you will not get stuck. Why not? Well, because you came in and you left. So if you're a vertex other than V, if you've been there before, that meant you came in and you left. So you use 2 of the edges every time you got to a vertex, you use 2 of its edges. And that vertex had an even number of edges. So every time you subtracted 2. So this new time that you want to get to this vertex, either the degree is 0, in which case you can't get to it because the remaining degree is 0 and you can't get to it, or it's still an even degree. So when you get to it and use one of those edges, there's still a way out. So you can't get stuck at any vertex other than V because you can always leave. And so the only way to stop is to come back to V. Now, it's possible for you to come back to V and not get stuck and keep going, but eventually you'll have to get stuck, and the only place you can get stuck is at V. And then that gives you a circuit because you started at V, you took a walk, you didn't repeat any edges, and you ended up back at V. Now, this circuit, again, might not contain all the edges. In particular, your graph might not be connected. It might have different connected components, and so there might be a whole bunch of vertices or edges that you never visit. But there will be a circuit containing V. Now, our main theorem for this lecture is the theorem characterizing Eulerian circuits. When does a graph has an Eulerian circuit? And this is a very nice theorem because it's a very nice, easy characterization. If you have a finite general graph with no isolated points, isolated vertices are not relevant in terms of finding Eulerian circuits, then G has an Eulerian circuit if and only if it's connected and it has all even degrees. If you have a connected graph with all even degrees, then you have an Eulerian circuit. So if you believe that theorem, the original Konigsberg bridge problem, you can look at it and you say, well, there's a degree 3 vertex here, another one there, 1, 2, 3, 4, 5, another one here. In fact, all degrees are odd. It doesn't have an Eulerian circuit with a vengeance. So the answer is clearly no. Euler actually just proved one direction. That's the easier direction. And it's the direction you need for answering that the Konigsberg bridge problem, the answer is no. So we are assuming that G has an Eulerian circuit, and we want to show that then that means that G must be connected and has all even degrees. First of all, it must be connected because on that Eulerian circuit that's covering all the edges, all the vertices must be on it as well. So you can, on that circuit, you can go from any vertex to another. But every edge of G is in the circuit exactly once, because it's a circuit and edges are not repeated. So that means that for each vertex, you can pair the edge that comes in with the one leaving that vertex on the circuit. So the circuit, if it's visiting every vertex 10 times, then the degree of that vertex will be 20, because 10 times you came in and 10 times you left. Now we have to prove the other direction. The other direction is the more substantial direction, and it took about 100 years for Karl Hierholzer to prove it. In fact, his paper was published after he died, somewhat young. He died when he was 31. Would not have guessed that more than 150 years later, we would be talking about him and his result. So this time we have that G is connected and all degrees are even. And the question is that if you just, that's all you know, that it's connected and all the degrees are even, why will you have an Eulerian circuit? Why will the whole graph be just one circuit? The key idea is that you say, well, I'm going to start with the longest circuit in G. I mean, there will be some circuit because the degrees are even. We'll have some circuit. Pick the longest one. We're hoping that longest circuit contains all the edges, but we assume that it doesn't. This is a proof by contradiction. And then we'll show that we can, if that's the case, we can actually extend the circuit and make it longer. And then that would mean that it wasn't the longest circuit, and therefore something is wrong. And so what must have been wrong is that the original longest circuit must have contained all the edges. By the way, I say a longest circuit because there may be several. Just pick one. For example, maybe this is a part of my graph here that I have here on the right, and here's the longest circuit. That maybe this is the longest circuit that I found, that the edges in red. And what I'm going to do is I'm going to eliminate the edges of this longest circuit. So I'm going to take those red edges and drop them. When I do that, there will be some vertices that will be isolated. There will be just sitting there alone because they were sitting on this circuit and they were not connected to anything else. Get rid of those as well. The remaining graph, I'm going to call H, and I'm going to try to use it to be able to extend this circuit C. And note that each edge of G, each edge of the original graph G, is either in the circuit or in this remaining graph H, because that's the way we constructed H. We took the edges of C and dropped them and dropped some vertices, but no other edges, and every other edge was in H. So every edge of G is exactly in one of C or H. Now, it can't be in both, but it's in one or the other. Okay, so where are we at? G is connected and all degrees even. C is the longest circuit in G. H is the edges not in C and their vertices. And we're trying to see if we can extend the circuit C. Now, C is a circuit, and H has no isolated vertices. H has no isolated vertices because we dropped those isolated vertices. If you think about H, those vertices that it has, they're not isolated, but what's their degree? Well, from the original graph G, every vertex of H lost an even number of edges. Why? Because the circuit came in and left. That means that the degree of each vertex of H is even, because it used to be, the degrees used to be even, and we kept taking twos out. And so we took an even number of edges out of an even number of edges. And so what's left is even. And the degree is positive because H doesn't have any isolated vertices. And this was exactly what we proved the theorem about. We proved that if you are in that situation where every vertex of a graph, in this case H, is positive and even, then every vertex lies on a circuit. Okay, hold that thought for a second. C and H don't share any edges because the edges were partitioned. Some of them are in C, some of them are in H. But G is connected, is a connected graph. And so C and H must share at least one vertex Z. In the graph that I have, there's plenty of vertices that they share, but they have to have at least one common share. Otherwise, the graph would be disconnected. We know that Z lies on a circuit of H. So there's a circuit completely made up of edges in H that Z sits on. So you can start at Z, go through the edges of H, and come back to Z. You might not cover all of H, but you cover some of it. And what we can now do is extend the original cycle by inserting D, by splicing D at Z. So you start maybe at Z and go through C all along and come back to Z. But instead of stopping there, you go through D again and come back Z. And now this is a circuit because there's no repeated edges. It consists of all the edges in C and the edges of this new circuit, D, whose all of its edges were in the graph H, which did not share any edges with C. So you have a circuit. But it's a longer circuit than C, and C was supposed to be the longest circuit in C. So this is a contradiction. So what went wrong? What went wrong was that H really did not have any edges to begin with. When we got rid of edges of C and then isolated vertices, we weren't left with anything. That must have been what has happened, and therefore C is already an Eulerian circuit. So that proves that theorem, and it's a very nice theorem because a very nice, easy characterization, but the proof actually is what's important. Now, what about Eulerian trails? If I want to start at the vertex, go through all the edges exactly once, and come back to that vertex, I know that all the degrees have to be even and the graph has to be connected. But what if I drop getting back to the same place and I just want an Eulerian trail? We have a very nice theorem for that too, but actually the proof is what's really neat here. So you have a connected finite general graph. Let's say you have two distinct vertices, U and V of G, that you're interested in, and you want to know, can I go from U to V and have an open Eulerian trail? So Eulerian trail, again, means go through every edge exactly once. But I want to start at U and end at V. And the answer is that you can do that if and only if U and V are the only vertices of odd degree. So if you want an Eulerian circuit, you have all the degrees to be even. But if you want an Eulerian trail from U to V, then U and V can be odd, and in fact have to be odd, but those are the only ones that can have odd degree. Okay, what's the proof? And now you might think that we have to go back to and do a similar argument to the one we did before, but we don't have to. We're going to bootstrap what we had and prove this theorem. So hold on to your seats. So what we're going to do is add an edge to our graph, joining a new edge, adding U and V. Maybe U and V did not have an edge, so this is a completely new edge, but it might be that they already had an edge, and so we're adding a second edge, and that's okay because we're in a general graph, and we can have multiple edges. In fact, this is an example of a theorem that's easier to prove if you're proving a harder theorem, a more general theorem about general graphs, as opposed to for simple graphs. This theorem is also true for simple graphs, but if you wanted to prove it for simple graphs, I couldn't do this proof, because at this point you might say, well, I might not be able to add another edge because maybe there's already an edge between U and V. But because I'm thinking about general graphs in general, I can do that. If you do that, let's think about, what did we want? We wanted an open Eulerian trail from U to V. That's the same as saying that we want this new graph to have an Eulerian circuit. Why? Because if the old graph had an Eulerian trail from U to V, now we have this extra edge, and so we can go back from V to U and make an Eulerian circuit. Vice versa. If G prime, this new graph, had an Eulerian circuit, just take that new edge out, and you will have an Eulerian trail from U to V. So G having an Eulerian trail is the same as G prime having an Eulerian circuit. And Eulerian circuits, we just proved the theorem, then that means that G prime has to have all even degrees. But then that means that if you take that edge out, U and V are the only ones that are losing an edge, and so U and V are the only vertices of odd degree in G. And if you go back to that example that at some point we looked at, and I asked you if this was one circuit, meaning that does this graph have an Eulerian circuit? The answer is no, because it has two vertices of odd degree, 3 and 2. But now we know that because it has exactly two vertices of odd degree, it does have an Eulerian trail, but you have to start at 2 and end at 3, or start at 3 and end at 2. You can't start at 1 and end at 4 or something. You can't do that, or end at 3. A related topic, maybe actually a more important topic, is decomposing graphs into subgraphs. So let me give you a definition. G is a general graph, and I have a bunch of subgraphs of G. So subgraph is a bunch of vertices and edges of the original graph. But if you pick an edge, you've got to pick its vertices as well. You can't just have an edge with no vertices. Assume that each edge of G is in exactly one of these subgraphs. So in other words, you have partitions the edges into these subgraphs. Every one of them is in one of these, and none of them is in two of them. Then if you have that, then you say that you have a decomposition of G, or if you want to emphasize the fact that this is an edge decomposition, you have partitions the edges of G. So if you have an edge decomposition, note that these subgraphs do not share any edges, but they may share vertices. So as an example, look at this graph on the right here, bottom right here. So one way to decompose it is to have a red triangle, that red triangle, and then have a path of length 1, 2, 3, 4 with 5 vertices. This blue path and the red triangle are two graphs that give us a decomposition of that original graph. But you can do it some other way. For example, you can have two triangles, the blue triangle and the red triangle, and then one edge, the brown edge. So those would be decompositions of this graph. Finding decompositions of graphs is actually a very important and useful thing, especially in computer science in graph algorithms. The first theorem is that I want to tell you that if you have a circuit, maybe the whole graph is a circuit, or maybe C is a circuit in a general graph, then that circuit has the decomposition into cycles. You can always decompose a circuit into cycles. So how I'm going to prove that? I'm going to induct on the number of edges. So that means that I'm going to prove some base cases, and then I'm going to say that, okay, give me a graph that's the circuit, and I'm going to decompose it into cycles, but I get to assume that any circuit that has fewer edges can already be decomposed into cycles. If you're not familiar with strong induction like that, please watch my video on strong induction. So we're inducting on the number of edges. The base cases, I should really do just one edge, but just to be sure, I'll do if the number of edges are 1 or 2. In that case, we will have a general graph. So for one edge, how can you have a circuit? Well, it's just a loop. With two edges, you might have two loops joined at a vertex, or two vertices with double edges. And each those can clearly be decomposed into cycles. Now, assume the result is true for all circuits with fewer edges than C. This is our inductive hypothesis, that C is given to me, C has walked through the door, C says, I'm a circuit, prove that I can be decomposed into cycles. And I say, okay, I'm going to do that, but I'm going to assume that if there's any circuit that's smaller than you, smaller in the sense that it has fewer edges, then that can be decomposed into cycles. If C itself is a cycle, then, well, of course, I'm done. Otherwise, some vertex is repeated on the circuit. If it's not a cycle, why is it not a cycle? It's a circuit. Why is it not a cycle? That might mean that some vertex is repeated, because cycles are circuits without repeated vertices. So if that's the case, go look at that circuit C and choose a shortest walk on that circuit between two occurrences of the same vertex. Say, okay, well, this vertex is repeated again. What's the shortest walk that goes from this vertex to itself? That shortest walk must be a cycle, because if it's not a cycle, then you could have shortened it. So the shortest walk on a circuit between two occurrences of the same vertex must be a cycle. Take out the edges of that cycle and have a new graph. This is the cycle starts at a vertex on the circuit and comes back to it. If you take it out, what remains is still a circuit, but it's smaller. And because of that, by induction, you can decompose that smaller circuit into cycles. Now throw back the cycle that you took out, and you have a decomposition of your graph into cycles. So you take one cycle out, the rest are a smaller graph, so you have done it earlier via induction. Now you put this graph in, and you have your decomposition into cycles. When can you decompose a general graph into cycles? So if G is a finite general graph, G has a decomposition into cycles, if and only if every vertex of G has even degree. Again, this is if and only if, so it's a characterization. This is a very simple thing. A graph walks through the door. You want to know, can I decompose this into cycles? All you have to do is to check to see if all the degrees are even. And because we're wanting to decompose into cycles, but we're not looking for an Eulerian circuit, we don't have to assume that the graph is connected. As long as all the degrees are even, you can have a decomposition into cycles. Now, why is that? Pay attention to the proof. So one direction is the only if direction. So assume that you have a decomposition into cycles, then why is it that all the degrees are even? You should be able to do this yourself. Stop the video and tell me why this is, because we have seen this argument before. The argument is that if you take a vertex, x belongs to h of those cycles, and then the degree will be 2h, because every cycle will come in and leave. So the degrees will have to be even. But now what about the other direction? So assume that every vertex is even. Why can you decompose it into cycles? If every degree is even, the graph might not be connected, but every connected component is connected and every degree is even, and therefore it has an Eulerian circuit by the major theorem that we proved in this lecture. And then we know what we just proved earlier, that every circuit can be decomposed into cycles. So that Eulerian circuit can be decomposed into cycles. So that connected component can be decomposed into cycles, and you can repeat that for every connected component, and you have a decomposition into cycles. One final thing that I want to do as an example of how we use these ideas that we have been throwing around is maybe we'll ask the following question. First of all, every graph, you can decompose it into trails. I mean, the simplest thing to do is just make every edge is a trail, and just decompose the graph into as many trails as you have edges. That's not satisfactory though, because you're just using up too many edges. You might want to use fewer trails. So let's ask a particular question. What's the minimum number of open trails that you need to decompose K8? K8 is the complete graph on 8 vertices and all the edges that go through them. I want to use as few open trails as possible to decompose it. Maybe I can use one. If I can use one, then that's an Eulerian trail, but maybe K8 has that. And also, I want to know how to construct these. First of all, K8 has 8 vertices. All of them are odd degree. Therefore, it doesn't have an open Eulerian trail. So we can't just have one. And so here's the trick we do. We pair the vertices into pairs, like say this guy and that guy, this guy. It doesn't matter how. You just pair them, and you have 4 pairs. For each pair, you add an extra edge between them. So if I pair this vertex and that vertex, I put another edge in it. Now I get a multigraph. But this time, this multigraph still has 8 vertices. I didn't add any vertices, but every vertex now has degree 8 because I added an edge to every vertex. And now, because this graph has all even degrees, I know that it has an Eulerian circuit. But this is not the graph I wanted. That's not the K8. It's something else. But this new graph that has all these double edges has an Eulerian circuit. Now, take those extra edges out. And what will happen to that Eulerian circuit? This Eulerian circuit will get cut at 4 places. If you cut a circuit in 4 places, you will get 4 pieces, and each of those will be an open trail. And they will cover all the edges of K8, because the only things that you took out of that Eulerian circuit was those extra 4 edges that you had put in. So by adding those 4 edges, you got an Eulerian circuit. By taking them out, you get 4 Eulerian trails. This is nice. Now, you can't do the 3, because if you could, then that would mean that you have 6 vertices of odd degree. If all the edges were on these 3 trails, these 3 trails started from someplace and ended someplace, those would have odd degrees, and there would be 6 of them, but we have 8 such things. This is the end of this lecture. Please subscribe and like my video, as long as you like them, and as long as you want to be subject to videos like this on your feed. And keep hydrated at all times, and I'll see you at the next video.